Okay, let's talk now about the Taylor and the Maclaurin series. And let's start this off with an example so you can kind of get into what the concept of all this is going to be about. Now consider the functions f of x equals sine of x. And the idea here is I want to find sine of 0.2. I'm looking for f of 0.2 without a calculator. That's not an easy thing to do because 0.2 is not a common angle. Now, I may not be able to find what sine of 0.2 really is, but I should be able to get pretty gosh darn close to the thing. And I want to use a linear function. So I should be able to get pretty close with a linear function. Now, the idea here is I want to find a first degree polynomial approximation for f of x equals sine x about 0. So I want to do this about 0. Now what it means to be about 0 is I'm going to match x and y at x equals a. So here what I'm saying is that a equals 0. So if a equals 0, what I need to know is what is sine of a. In other words, what is sine of 0? And of course sine of 0 is 0. So what I've done is I've said, hey, a is a particular value of x, and I know what sine of x is going to be at 0. So what I just did is I'm going to force my linear function, my first degree polynomial, to go through the point 0, 0. Because I know sine of 0 is 0. So they will both share that same point. The linear approximation and the original function sine of x will be equal to each other when x is 0. The other thing that means is that I want to match the slope at x equals a. So whatever the slope of my original function is at, in this case, 0, because a equals 0, whatever the slope is of my function at 0, that's what I want the slope of my linear approximation, my first degree polynomial, to be. So what I need to do is take the first derivative, d dx, of the function I'm trying to approximate. So d dx of sine x, which is cosine of x, evaluate that at x equals 0, and of course I get 1. So now I know that the slope is equal to 1. So knowing the slope and the point, or a point that the line is going to pass through, I can use this form of line, which tells me y minus 0 equals m, which is 1, times x minus 0. See here and here. Oops, that wasn't much of an arrow. That's my point right there. So that tells me that my first degree polynomial approximation is actually the line y equals x. Well, if I quickly draw sine of x, I'll go a little bit farther. There we go. Here I match both the linear approximation and sine of x go through 0, 0. So I'm going to use this line, y equals x, to approximate sine of x. And you can see by the way I drew it, even though I kind of drew it a little bit off, near 0, the line and sine are very, very close to each other. So the line looks like it's going to make a pretty good approximation. When I get close to pi over 2, I can see clearly that my linear approximation and the function is going to separate dramatically. So at some point, it does not become a very good approximation. But near this value that I'm expanding it or creating it about, near that value, this should be a very good approximation. Okay, so let's go ahead and take a look at doing the same thing, only this time I want to go about a equals pi over 2. So I'm going to do the exact same thing I did before. I'm going to take a look at d dx of sine of x, which equals obviously cosine of x. I'm going to evaluate this at x equals pi over 2. That's this value a that I'm building this about. And that is equal to 0. So I know my slope will be 0. Now what is sine of pi over 2? So I want to match it at x and y. I want to match those points. Well, sine of pi over 2 equals 1. So I know that I have the point x equals pi over 2, y equals 1, with a slope of 0. So I can use that same form again, y minus y1 equals the slope times x minus x1. Well, I'll get y minus, see, y1 is 1, so y minus 1 equals slope, which is 0, times x pi over 2. Oops, I'm sorry, x is x. x1 is pi over 2. Well, that tells me that y minus 1 equals 0, or that y is equal to 1. So if I graph this to see what's going on here, that's sine of x. And over here is pi over 2. So I've matched my linear function at this point. My linear function goes through that point. It has a slope of 0, so the line y equals 1. So my linear approximation will look like this. So you see at x equals pi over 2, my linear approximation and the original function match each other. So the approximation is actually exact. But as soon as I get away from pi over 2, immediately this becomes a horrible approximation. It's a miserable approximation. Whereas compared to the other one, that linear approximation we did a little while ago, which is roughly something like that, roughly in this area, I'll get a halfway decent approximation. But as x increases, clearly my approximation becomes worse and worse and worse. But again, we centered it about 0. We expand this about 0. Both the linear approximation and the function match each other at 0. So when x equals 0, that first linear approximation, which is based on expanding it about 0, was exact. There was no approximation. It matched exactly. Okay, so to prove our approximation, what do we want to do? Well, first of all, we want a starting point of the approximation to be equal to the original function. That was what we did. We said we're going to match x and y. So in other words, if I'm going to take this thing and expand it about 2, I'm going to approximate some function with another function about 2. That means I need to be able to figure out what both functions are at 2. I need to have that starting point. Got to have it. So let's see, given some arbitrary function, let's say we have something that looks like this, whatever it is. And I'm going to, here's my a. So I need to know what the original function is at that value. Then this next point here is I want the slope of the approximating function to match the slope of the original function. So whatever the slope is of this function, that's what I want the slope of the approximating function, that linear function, to be. What if I take it a step farther? What if I look at the second derivative? And as you know, the second derivative will tell me about concavity. So if I do a second derivative, and then I can take the concavity of the approximating function to match the slope of, well actually this should say concavity right here. So the concavity of my originating function, I want to try to match the concavity of the the function I'm trying to approximate. Well, here at this point, I guess this could be concave down. It's hard to tell where I drew it. So I'd want perhaps a quadratic function, something that I can adjust the concavity on to do this approximation with.